Imagine your company launches a new feature and the feature actually improves conversion rate, not by 20% or 10%, but by 0.5%. Tiny, almost invisible. Now here's the scary part. Even if the improvement is real, your experiment may still completely miss it. Not because analysis was wrong or product failed, but because experiment was never designed to detect changes that small. And this is one of the most expensive problems in experimentation. Companies reject profitable ideas. Teams kill good features. Analysts conclude no statistically significant effect. When the truth was, experiment simply wasn't sensitive enough. And the concept that controls this sensitivity is called minimum detectable effect. In short, MDE. MDE determines what size improvements your experiment is capable of detecting. And once you understand MDE, you start seeing experimentation completely differently. Because experimentation is not just about finding effects, it is about deciding what effects are even worth detecting in the first place. Welcome back to Sheetal's Data Days. I am Sheetal, and in this video, we will break down these topics one by one. By the end of this video, you won't just understand what MDE means, you will understand why MDE is really a business decision disguised in statistics. So, let's start with the core question. What exactly is MDE? MDE or minimum detectable effect is the smallest improvement your experiment is designed to reliably detect. In simple terms, MDE answers question what is the smallest change we actually care about finding. Suppose your website currently converts at 5%. You launch a redesign. Now imagine several possible outcomes. Conversion rate increases from 5% to 7%. That is 2% point increase. But relative to original 5%, that is actually 40% relative improvement. And that is the big effect. The signal stands out clearly from noise. So statistically, this is usually easier to detect. Now suppose conversion increases from 5% to 5.2%. That is only 0.2% point increase. But relative to original 5%, it is still 4% relative improvement. And at massive scale, even tiny relative improvements like this can generate millions in additional revenue. This is where many beginners get confused. In experimentation, improvements can be described in two different ways: absolute change and relative change. Absolute change measures direct difference between two percentages, and relative change measures how large that difference is compared to starting point. And businesses often care more about relative impact because a small absolute increase can sometimes represent meaningful improvement in performance. That is why same experiment result can look small from one perspective and important from another. Now here's the key idea. If your MD is large, experiments can detect changes faster because large effects are easier to separate from randomness. But if your MD is tiny, experiments become dramatically harder because tiny effects can easily hide inside normal variation. This creates one of the biggest trade-offs in experimentation. The smaller the effect you want to detect, the more users you need, the longer experiments must run, and the more expensive experimentation becomes. So, MDE is not asking what changes are possible. It is asking what changes are worth detecting. And that is not just statistical decision, it is business decision. But to truly understand why smaller MDEs become so expensive, we need to understand relationship between signal and noise. Imagine standing in noisy room. Someone across room whispers hello. You probably won't hear it. Now imagine they shout hello, easy to detect. That's exactly how experiments work. Large effects are loud. Small effects are whispers hidden inside randomness. In experimentation, effect is signal and variability is the noise. MDE determines how loud the signal must be before your experiment can reliably notice it. A smaller MDE means your experiment becomes more sensitive, but higher sensitivity requires much more data. And this leads to one of the most surprising truths in statistics. Tiny improvements are statistically very difficult to detect. And this creates one of the most important trade offs in experimentation. Suppose detecting 4% improvement requires 2000 users. Now, suppose you want to detect 2% improvement. Most beginners assume maybe we only need double the data. But in reality, you may need 4 times more data because as effects become smaller, signal and noise start looking similar. Imagine trying to hear a whisper in crowded room. The whisper is the effect, crowd noise is variability, and separating two becomes dramatically harder. This is the part that surprises most people. Relationship between MDE and sample size is not linear. Reducing MDE slightly can explode amount of data required because tiny effects require extremely precise measurement and precision requires many more observation. So here's the fundamental trade-off. Smaller MDE means larger sample size and larger MDE means smaller sample size. If your experiment only cares about detecting huge improvements, you don't need much data. Large effects stand out quickly. But if your business cares about tiny improvements, experiments become slower, more expensive, and much harder to run reliably. Because detecting subtle changes requires higher statistical sensitivity. And the cost is not only sample size. Smaller MD experiments often require longer run times, more engineering coordination, slower decision making, more opportunity cost. Because experiment needs enough evidence to confidently separate real signal from randomness. This is why companies like Google, Amazon, Netflix sometimes run experiments on millions of users. Not because analysts love giant datasets, but because detecting tiny improvements is incredibly difficult statistically. And at massive scale, even tiny improvements can generate enormous business value. So, choosing MDE is really balancing sensitivity versus speed versus cost versus business value. MDE is not just statistical setting, it is strategic business decision. So, how do smart teams decide what MDE is actually realistic? Before running any experiment, teams must decide what level of improvement would actually justify action. Not every detectable improvement is meaningful, and not every meaningful improvement is easy to detect. Every experiment carries a real operational cost. Imagine your engineering team spends 3 months building complex recommendation system. In that situation, a tiny 0.1% conversion lift may not justify engineering effort, maintenance cost, and opportunity cost. So, in high cost projects, teams often choose larger MDs because they only care about large, meaningful wins. Now, compare that to changing button text, improving a headline, or tweaking checkout copy. These experiments are cheap to run, so even tiny improvements may be valuable. And that means smaller MDs can make sense. And this is where many analysts make major mistake. Some teams choose unrealistically large MDA values simply to reduce sample size. For example, let's only detect 20% improvement. Why? Because smaller experiments are cheaper, faster, easier to run. But if realistic improvements are usually 1% or 2%, then the experiment becomes almost useless because it was never designed to detect kinds of improvements that actually matter. Good MDE choices should come from historical experiments, business impact, domain knowledge, realistic expectations, not from trying to make experiments artificially smaller. A good MDE reflects smallest improvement that would genuinely change business decisions. But there's another hidden challenge underneath all of this. MDE is deeply connected to variability. When data becomes noisier, tiny effects disappear more easily. Imagine tracking conversions on an e-commerce platform. On Mondays, marketing campaigns run and conversion spikes to 12%. On Thursdays, traffic drops and conversion flatlines to 2%. That constant fluctuation over time creates enormous background noise, and heavy noise easily swallows a tiny, subtle 0.5% true improvement. So, highly noisy systems usually require much larger sample sizes to detect same MDE. MDE is never isolated. It always interacts with variability, power, alpha, and sample size. And when analysts misunderstand these relationships, experiments often fail before they even begin. Mistake 1: Unrealistically large MDE. Choosing huge effects just to reduce sample size. Mistake 2: Unrealistically tiny MDE. Trying to detect effects so small that experiment becomes impractically expensive. Mistake 3: Ignoring business value. Detecting statistically significant changes that are financially meaningless. Mistake 4: Forgetting variability. Tiny MDEs become extremely difficult in noisy systems. Mistake 5: Copying industry defaults. Using random MDE values from blog posts instead of using business specific reasoning. And different industries solve these trade offs very differently. Startups often prefer larger MDEs. Why? Because they prioritize speed, fast learning, rapid iteration. Large tech companies often care about tiny MDEs because even 0.1% improvement can generate millions at scale. In medicine, small improvements can literally save lives. So, experiments may target very small MDEs with extremely large sample size. Manufacturing focuses heavily on consistency, defect reduction, precision. So, even small improvements may matter operationally. But here's something many beginners misunderstand. Statistical significance does not automatically mean result is important. With enough users, you can detect absurdly tiny improvements. Example, a 0.01% increase in conversion rate. Statistically significant, but business wise, possibly meaningless. And this is exactly why MDE matters. Because MDE forces teams to think before experiment. What size improvement would actually matter? Not just what can we detect. And this connects directly back to power analysis. Because MDE is one of the core inputs used to calculate sample size. Power analysis combines alpha, statistical power, variability, and MDE to calculate required sample size. So, MDE directly controls sensitivity of your experiment. Smaller MDE means larger sample sizes, longer experiments, higher cost. Larger MDE means smaller experiments, faster decisions, lower sensitivity. So, these concepts solve two different problems. Power analysis answers how much data do we need? MDE answers what size improvements are worth detecting? And together they determine whether your experiment is practical, reliable, and actually useful for decision making. So now let's bring everything together. MDE stands for minimum detectable effect. It defines smallest improvement your experiment is designed to reliably detect. Smaller MDE requires larger sample sizes. Larger MDE requires smaller sample sizes. MDE is not just statistics. It represents business priorities, sensitivity, core tolerance, and decision making strategy. Tiny improvements are not cheap to detect, and that's why experimentation is fundamentally an optimization problem. And here's the deeper truth behind all of this: experiments are not magical truth machines, they are detection systems, and every detection system has limits. MDE defines how small a signal your system can realistically detect. If the signal is smaller than that, truth may still exist, but your experiment will never see it. And that is why great analysts don't just ask, is there an effect? They first ask, what size effect is realistically detectable? If you found this video helpful, don't forget to like, share, and subscribe to Shital's Data Desk. Thanks for watching, and I will see you in next video.